Welcome to another episode of AI Talks with Chris and Nita. Today, we're going to dive into sequence-to-sequence models. Seq2Seq for short.
Yeah, 66. These are, well, they're neural networks, right?
Right. And they're really good at turning one sequence of data into another one.
Exactly. Think about taking maybe an audio clip.
And getting a transcript out.
Precisely. Or translating languages,
Yeah.
taking English, getting French, that kind of transformation.
Super useful stuff. So our goal today is just to quickly unpack what these models are really about.
And why they're so important, yeah.
Yeah.
At their heart, C2SIG models tackle this problem of mapping sequences.
Where the input and output might be totally different lengths.
Exactly. You ask a short question, you might get a much longer answer. That kind of flexibility.
And it does this with two main parts.
That's right. A two-part structure. You got the encoder, and then you got the decoder.
Okay, so let's start with the encoder. What's its role?
So the encoder, its job is to read the input sequence. Let's say a sentence in English. It goes through it step by step, word by word, or maybe token by token.
And while it's reading...
While it's reading, it's basically building up an understanding.
Yeah.
It updates its internal memory.
The hidden state, right.
Exactly, the hidden state. It keeps getting updated with each piece of input it sees, sort of summarizing as it goes.
So once it's read the whole sentence, that hidden state holds the summary.
Well, it takes that final hidden state, or sometimes a combination of states, and compresses it. It distills it down into what we call a context vector.
A context vector, like a little package of meaning for the whole input.
Pretty much. A fixed-length package, actually, which was a bit of a limitation early on.
Oh, right. Because long sentences might get squashed too much?
Yeah, potentially losing information. That's where later advancements like attention mechanisms came in. They really helped.
Ah, attention. That lets the decoder look back at specific input parts. We should probably cover that another time, though.
Definitely. But for the basic CT-SIG, this context vector is the key handoff.
Okay, so context vector is ready. What does the decoder do with it?
The decoder takes that vector. That's its starting point, its initial instruction, if you like.
To start generating the output.
Exactly. Say the French translation. And just like the encoder, it works step by step.
Producing one word or token at a time?
It generates the first word, then uses that information plus the context to generate the second, and so on.
And it needs to remember what it's already said, I guess.
Absolutely. That's why these decoders, and encoders too, often use things like recurrent neural networks, RNNs.
Or LSTMs, long short-term memory networks.
Right, LSTMs or GRUs. They're types of RNNs specifically designed to handle sequences and remember information over longer periods. Those internal loops are key.
Okay, that makes sense. Now, I've heard about something called teacher forcing during training. What's that about?
Yeah, teacher forcing. It's a training technique to help the decoder learn faster and more accurately.
Give us some help.
You do. Instead of letting it use its own previously generated word to predict the next one, which might be wrong early on.
You feed it the correct previous word from the actual target sequence.
Exactly, like showing a student the right answer for the previous step to guide them on the next one. Helps stabilize the learning.
Gotcha. So, quick recap. Encoder reads and summarizes into a context vector. Decoder takes that vector and generates the output, step by step, often using RNNs or LSTMs.
That's the core idea, yeah. It's a really powerful framework.
And the applications are pretty wide, right?
Oh, definitely. Machine translation's the classic example, as we mentioned. Google Translate, DeepLL, lots of those use Seq2Seq principles.
What else? Text summarization.
Yep. Training a model to read a long document and spit out a short summary. That's a sequence-to-sequence task.
Makes sense. Shorter sequence out than in.
Right. And speech recognition, too. Taking the sequence of audio features.
And outputting a sequence of words. Text.
Exactly. Especially powerful when combined with those attention mechanisms we mentioned briefly.
And even image captioning. That seems a bit different.
A little variation, yeah. You first use a different kind of network, like a CNN, to extract features from the image, creating a sort of context.
And then a decoder, probably RNN-based, generates the caption sequence.
You got it. It generates the description word by word based on the image context.
Wow, okay. So it really is this fundamental building block for a lot of AI tasks involving sequences.
It really is. It provides this elegant way to handle inputs and outputs that are sequential, even if they don't match up neatly in length or structure.
So thinking ahead, these models handle one input sequence to one output sequence really well. Here's something to think about for you listening. What happens when we push these models further? How might they evolve to handle, say, multiple types of sequences all interacting?
Ooh, like understanding a video.
Yeah, like understanding the video frames, the audio track, maybe subtitles or a transcript all at once, and generating something based on all of it.
Multimodal sequence processing. That's definitely a fascinating area. Huge potential there.
Feels like a whole new level of understanding, something to keep an eye on.